Okay, well, why don't we get started? So welcome back, everyone, for the next session this morning or this afternoon or whatever time it is where you are. My name's Stephen Bartlett, and it's my pleasure to chair this session today and get to introduce Andrew Dzurak, Professor Andrew Dzurak from UNSW Sydney. Now, Andrew is a world expert in silicon-based quantum computing and nanoelectronics. He is a UNSW Scientia professor and an ARC laureate fellow, focusing on the development of quantum processor chips based on silicon-CMOS technology. And he's also, I can tell you, a fantastic person to collaborate and work with. Andrew and I have been working with each other for a number of years, and it's been great fun. I'm looking forward to his talk today on silicon-based quantum computing from laboratory to industrial manufacture. Over to you, Andrew.
Thanks very much, Stephen, and thank you to Stephen and all of the organisers for inviting me to give this talk. And I should reciprocate by saying that Stephen Bartlett is a fantastic person to collaborate with as well. I've been enjoying that collaboration for quite a long time now. Stephen and the organisers asked me to give an overview talk, which is what I've put together here to give a bit of the history of the development of silicon-based qubits and quantum computing, but also looking into the future of what might be possible in terms of the scalability of this technology, and also what some of the perhaps the major challenges are looking forwards. So I'd like to begin by acknowledging the amazing research group that we have at UNSW working on this project. And I've listed here our current postdoctoral researchers and also my faculty collaborators, Henry Yang and Anna Laut, and all of our fantastic graduate students. But also at the bottom, I've listed a number of our former team members from the last 3 years who have contributed to a lot of the work that I'm going to show today, and who I'm pleased to say we still keep in very good touch with and collaborate with. Also, I'd like to acknowledge some really important collaborations that I have both in Australia and around the world, particularly at UNSW, my long-term collaborator, Andrea Morello, who a lot of the early work in this talk is going to involve work that I did together with Andrea a few years back, and more recent existing collaborators in the School of Physics, Demi Kelser and Alex Hamilton. I've already mentioned Anna Laut in electrical engineering, and at Sydney, Stephen, who we've already seen, and David Riley, who are important collaborators, and other collaborators all around the world. So thank you to those. So I'll begin only one sort of intro slide, really reminding us that Feynman's original vision for using quantum states to perform computations can use any quantum 2-level system, or even many-level system, of course, but traditionally a 2-level system. And all of us are very familiar with the different implementations I've got on the screen here. Obviously, superconducting qubits and ion trap qubits are the technologies that are by far the most advanced in terms of number of qubits and the sort of operations that have been performed. But we saw, in fact, just this week, the impressive results out of China of work done with photon-based qubits. And so there's great potential for those as well, of course. But my talk today is about silicon, and the motivation for looking at silicon is the fact that we know that modern silicon microfabrication, CMOS technology, allows upwards of 1 billion transistors or memory elements, either processing elements or memory elements, to be integrated onto simply a square centimetre of silicon using advanced lithographic technologies and manufacturing processes. Now there's many billions, 100 billion processing or memory elements on a single chip that we use today. And so people in this audience will be very familiar with the fact that if we're going to have fault-tolerant systems that are able to tackle really challenging and very interesting problems, that is one of the great promises of quantum computing, then we know that we're going to need ultimately many millions of qubits and very likely billions as well. And so silicon provides a very appealing route from the perspective of being able to imagine utilizing that high density of qubits and interconnectivity, and also the ability to potentially leverage existing classical electronics that can be integrated side by side. Just briefly, I think that most of you in the audience are aware of the sorts of investments that are being made around the world in quantum computing. I've listed some of the biggest companies here, Google and IBM obviously working on superconducting qubits, Microsoft on topological qubits. Intel are looking at both superconducting and silicon qubits. And I just want to mention that here in Australia, we have a company that many of you would know about called Silicon Quantum Computing. Actually, I have to apologize, I haven't updated their logo to their new logo here, but this is a consortium that was spun out of the University of New South Wales and involves investments from Australian government, New South Wales state government, and Telstra and Commonwealth Bank, which are major corporations in Australia. And that's a very major effort now pursuing research in silicon-based qubits. And much of the motivation for that work came out of work at UNSW, which I'm going to talk about now. So the original idea of using silicon as a host for qubits goes back to this paper on the left here from Bruce Kane, who was a postdoctoral researcher at the time at the University of New South Wales in the late 90s. And he published this paper which is now very well known, in which he proposed the idea of using individual phosphorus atoms embedded in a very pure silicon host chip, and using in Kane's original vision the nuclear spin of the phosphorus nucleus. So phosphorus nuclear spin has a spin of 1/2, and so therefore it's an ideal two-level system. And what Bruce recognized right back at that time was foundational work on spin resonance in semiconductors that was done in the 1950s, which showed that coherence times of both the nuclear spin and the electron spin could be very long compared to the sort of times that could be needed to operate gate operations. And so this very favorable ratio of coherence time to gate operation time was recognized as a major physics advantage of using silicon as a host. But it was this other aspect of the potential compatibility with CMOS manufacturing that really then gave it this extra leverage. You have both the physics advantages, but you also have the manufacturability advantages. And so this is what Kane recognized back then. It's what now many companies and investors have recognized about silicon as a great potential for future quantum computing. And these two facts hold true today and maintain the enthusiasm in this technology. Now, going back to a little bit of the history of the development of silicon qubits, I want to note that when Kane originally proposed his vision, he was originally thinking about using scanned probe technologies in order to position these individual phosphorus atoms. Because of course, while it was a beautiful idea that Kane came up with, the idea of having individual atoms as qubits and controlling those, as shown on this previous slide, using metallic gate electrodes to manipulate the electron wave function, was really well beyond anything that our industry was working with. I mean, phosphorus is a standard dopant in silicon. It's used to provide conduction electrons to make transistors work. So it's well known in the industry, but you know, normally this is done with many thousands or millions of phosphorus atoms in the source and drain of the transistors, and certainly not individual atoms. And so technologies had to be developed to realize this idea of single atom qubits. And the one that Bruce Kane was thinking of at the time, and the one that was the first one pursued at UNSW, was this technology whereby one can take a very clean silicon crystal, coat it with a monolayer of hydrogen atoms, and then use the scanning probe tip to remove individual atoms to expose dangling bonds. And then phosphine gas can enter this into the vacuum chamber, and the phosphorus from the phosphine can bond to those dangling bonds. And then with an anneal step, those can be buried into the surface. The hydrogen can be removed, and then this can be overgrown with silicon. So this original idea, dating back to the late 90s, was then developed in real experimental demonstrations at UNSW in the early 2000s. And this work has since then really been championed by Michelle Simmons at UNSW. An alternate approach to configuring individual phosphorus atoms in silicon was a technology developed by Professor David Jamieson at University of Melbourne and ourselves at UNSW. And the idea here was to use a more conventional way of putting phosphorus atoms into the device, and this is ion implantation. So ion implantation, where you accelerate phosphorus ions and fire them into the chip, is the standard way that phosphorus and other dopants are put into silicon devices in the microelectronics industry. What we devised was the idea of fabricating particle detectors, ion impact detectors, in situ into the chip. And this was demonstrated in this paper in 2005 in APL, where it was shown that low energy 14 kilo-electron volt phosphorus ions, when they impinge into the chip, could be detected in this PIN detector structure, and one could register these impacts with high fidelity. This work's since been continued by David Jamieson in collaboration with Andrea Morello's group, and they've recently shown some really outstanding new results in the ability to count these atoms into the device. Just spend one more moment talking about the work of Michelle Simmons and her group at UNSW. This work has achieved a range of very, very impressive demonstrations, including making a single atom transistor. This is a single atom positioned between a source and a drain. This source and drain is fabricated using this scanning probe technology to create dense regions of phosphorus atoms here. In this paper in Science from 2012, Michelle's group showed the ability to have a conducting wire made of phosphorus atoms only 2 atoms wide. And more recently, her group have demonstrated operation of coupling between 2 spin qubits in silicon. So I won't spend more time working on talking about this, but there's plenty of work in the literature, and indeed the company Silicon Quantum Computing are focusing on this particular approach of silicon qubits. I want to talk now more about the work based on this ion implantation approach, championed originally by David Jamieson and now led experimentally by Andrea Morello at UNSW. This is the technology that really produced all of the initial demonstrations in silicon qubits and still has the highest fidelity silicon-based qubits known today. Really, after the original breakthrough of working out how to implant the ions, the next big breakthrough was the first demonstration of spin readout in silicon. And this was demonstrated in 2010. So it took a good decade of developments of device development and configuring this with this single ion implantation in order to get to the point where it was possible to actually demonstrate the readout of a single spin, because of course, quantum operations are only possible if we're able to do readout. And so this work published in Nature back in 2010, I'll just highlight one key aspect of it and describe the basic physics. So this little cartoon here shows the 2 spin states of an electron bound to a single phosphorus atom in a nanoelectronic device. And so we have spin down and spin up states separated by the Zeeman energy in a DC magnetic field of around, in this case, 1.5 Tesla. Next to the single atom, if I go back to the cartoon over here on the previous slide, so in this device, the atom was implanted into the silicon, And you can see this grey metal structure. This is aluminium electrodes that are fabricated using nanolithography, in this case electron beam lithography, on the surface of the silicon chip. And this blue region represents a number of electrons that are confined underneath this gate electrode, and this forms the island of a so-called single electron transistor device. And this single electron transistor device allows one to pass a macroscopic current that can be monitored outside the chip. And the measurement of the spin on this single atom is done by monitoring the current through this single electron transistor. So if we go now back to the next slide, this data here, taken from this paper in 2010, is showing the current measured between 0 and 1 nanoamp through that transistor device on the chip as a function of time. So sorry, this time's been cut off. This is up to 500 microseconds here on this time scale. And so what is done in this experiment is that if the electron is loaded with a random spin in this experiment, and then the Zeeman energy levels are positioned so that they straddle the Fermi energy in the island of this single electron transistor. And what that means is that only an electron spin up has sufficient energy to tunnel into the island of the single electron transistor, or SET for short. Now, when that happens, that then allows current to flow through the transistor, and so we see a sudden uptick in the current of the transistor, which can be monitored. A short time after that, just a couple of microseconds, depending on the tunnel rate, a spin down electron from that transistor will tunnel back onto the island, and after that, further current in the SET is blocked, because now this electron, which is spin down on the atom, can no longer energetically tunnel into the transistor. And so once the electron is tunneled off, the current is turned off. So what this provides is a very high fidelity fingerprint of the state of the spin on a single atom. And this was an incredibly important enabling result. It also showed in this experiment that the spin lifetime of the electron on this single phosphorus atom was many seconds, so effectively incredibly long compared to any of the operation times that were required for qubit control and readout. So once readout had been demonstrated, it was then relatively possible. I think I have a question. Let's see if I can. Can I just ask the moderators, are we planning to do questions throughout, or are we holding questions for the end? Is there a preference?
That's a good question, Andrew. I suggest we leave our questions to the end.
Yeah, I think
it's difficult in this forum.
Yeah, I think so. So I'll answer all those questions at the end. So returning to this paper published 2 years later, what our groups showed, and this work really championed by Andrea Morello, was that it was possible then, having readout in place, to employ a microwave AC magnetic field. So this is in the gigahertz regime, tuned to this Zeeman energy splitting, and it was possible to demonstrate Rabi oscillations in the spin of an atom bound in this nanoelectronic device. And then just 1 year later, and the PhD student who worked on this, Jared Pla, is now, I should mention, a faculty member at UNSW. Jared, Andrea, and our teams showed that it was possible to obtain very high fidelity control now of the nuclear spin. So this was actually, so what you're seeing here are Rabi oscillations, very high fidelity Rabi oscillations of the phosphorus-31 nuclear spin as originally envisaged by Bruce Kane. Now, the way that this is done is using an on-chip transmission line. So this is a transmission line that's been designed using microwave engineering to deliver a reliable AC magnetic field. So there's an AC current that's passed through this line, and then it produces an AC magnetic field around it, which then is used to rotate both the electron spin and the nuclear spin. And this was designed to be broadband, so it could operate all the way from megahertz up to gigahertz. So in the gigahertz regime, we perform electron spin resonance to control the electron spin. In the megahertz regime, we perform nuclear magnetic resonance to control the phosphorus-31 nuclear spin. And so with these demonstrations, it really showed that it was possible in nanoelectronic devices to control individual spins on individual atoms for the first time, essentially atom-based electron spin resonance and atom-based nuclear magnetic resonance. Now, one of the challenges still at that time was that I showed you very nice Rabi oscillations of the nuclear spin that I'll show you in a moment. The electron spin Rabi oscillations were not very good. Fidelity of those was really only around 70% or so, really quite poor. And the reason for that is because in naturally occurring silicon, around 5% of the atoms are the nuclei are spin bearing. So most silicon atoms are silicon-28, which has 0 nuclear spin, but about 4.7% of them are silicon-29, which have a nuclear spin. And these nuclei undergo flip-flop interactions, which fluctuate the local magnetic field, which then effectively cause decoherence of both the electron spin and the nuclear spin. And it's particularly harmful to the electron spin. So fortunately, the solution to this is simply to isotopically enrich the silicon. This can be done using standard centrifuge techniques, or there are other laser-based purification techniques that can be used. And indeed, this idea of using silicon-28 was originally envisaged by Bruce Kane right back in his original paper in 1998. And so what we did, and this was an important partnership with Kohei Ito in Japan, Kohei provided us silicon wafers that were mainly natural silicon, but which had around about 1 micron of silicon-28 that was coated onto the surface of the wafer. And then we made exactly the same device 2 years after our original qubit operation. And up here on the top right, this shows the relatively poor Rabi oscillations dying off in around 1 microsecond in natural silicon. But what you see here is an electron spin qubit now in silicon-28, enriched silicon-28, and you can see that the coherence remains well over 100 microseconds. In fact, electron spin coherence times are now of order 1 second when one employs dynamical decoupling measurements. And in fact, in this silicon-28, the nuclear spin of the phosphorus nuclear spin was shown to remain coherent for 30 seconds when using dynamical decoupling. So incredibly long coherence times demonstrated. This result really then showed that with isotopic enrichment, one can get extremely high fidelity for silicon-based qubits. It was a very, very important result. So I'm going to leave talking about single atom qubits, either ion implanted or STM-fabricated now, and because while this technology has very high fidelities, the challenge of manufacturing remains. And of course, both my colleague Michelle Simmons and her colleagues are working on approaches to create long arrays or large arrays of this type of either scan probe or ion implanted technologies. But all of these are still in development and not yet effectively mass manufacturing techniques that are available in industry. And so I now want to turn to a different approach to making silicon qubits, which can leverage this mass manufacturing approach that we see in this picture from, in this case, an Intel processor chip. And it came from ideas that date back, in fact, to the same year that Kane published his paper in Nature. And this was work from Daniel Loss and David DiVincenzo, who proposed the idea of using quantum dot devices, which at the time were primarily being investigated in gallium arsenide, and using those as spin qubits. And in fact, the groups that first demonstrated this type of qubit using quantum dots in gallium arsenide were one group in Harvard, led by Charlie Marcus, with Jason Petter being the lead investigator there, and Jason Petter has continued this work in silicon to this day. And also the groups of Leo Kalvenhoven and Leven van der Sijpen at Delft, and Leven van der Sijpen continues to do great work now in silicon these days. So both of these papers were in gallium arsenide. This is a double quantum dot using gate electrodes to provide corrals for single spins to be located in potential wells. And they're able, via different techniques, to manipulate the spin. I'll come into spin manipulation again a little later. But as I mentioned, both of these were in gallium arsenide because that was the platform, because it's has a very low disorder interface between gallium arsenide and aluminium gallium arsenide. And so these were low disorder structures that could give very nice potentials for the electrons to sit in. Most work in the 1990s and the early 2000s focused on gallium arsenide for nanoelectronic devices and mesoscopic devices. However, a major problem with gallium arsenide is that there's no nuclear spin isotope of either gallium or arsenic. And so there's constant disruptions from the nuclear spin bath, which damages the fidelity. And although work has continued to use dynamical decoupling to improve fidelities, obviously by working in silicon, one can remove that issue and have a significant advantage. And so in fact, most of the groups who were originally working on qubits and gallium arsenide have now migrated across to study quantum dots in different silicon technologies. And the silicon technology actually that has received so far most of the interest to date, and certainly initially, was a variant of the gallium arsenide, aluminium gallium arsenide heterostructure, and this is the silicon germanium heterostructure. And in this configuration, and I won't go into the details, but this shows one of the layer structures. The general idea is that the quantum dots are confined in a silicon quantum well, buried in an epi layer, and a barrier of silicon germanium is created above, and the electrons get held below. And then one can configure quantum dots using surface gate electrodes. And there are a number of demonstrations dating back to 2012, this first paper from HRL Labs in the US, where they, in natural silicon, showed control of, in this case, what's called a singlet triplet qubit. And they then continued 3 years later to show improved control and coherence in isotopically enriched silicon-28. There are a variety of other approaches being explored around the world in silicon germanium. This approach, developed from the University of Wisconsin-Madison, group led by Mark Erickson, and with theory support from Sue Coppersmith, who recently, a couple of years ago, moved to UNSW in Sydney. This hybrid approach of using a charged spin hybrid qubit has shown a number of great strides over the past 5 to 6 years. An alternative approach is to use a on-chip micromagnet. So by fabricating a micromagnet on the surface of a quantum dot device, one can create an artificial, effectively spin orbit coupling, so that when one moves an electron within a magnetic field gradient, one can electrically move the electron around, simply applying a microwave signal to a gate electrode, to move this electron in the static magnetic field, and that creates an effective spin resonance. This is called either electron dipole spin resonance or electrically driven spin resonance. And so Lieven van der Sijpen's group in Delft and Siego Tarucha's group, originally at University of Tokyo, now at RIKEN, have really been the leaders of this technology. And also more recently, Jason Petter has been using this technology as well at Princeton. And those groups have all made great strides in both 1 and 2 qubit gates using electrically driven spin resonance in silicon germanium. But I'm going to stop talking about silicon germanium now, and for the last half of the talk, I want to talk about a technology that is much closer to the technology that's used for conventional transistors in CMOS, and this is the MOS material system, and this dates back to work from our group at UNSW in 2007 with this paper in Nanoletters. Where we created a very high quality quantum dot structure, a very simple quantum dot in silicon using MOS manufacturing. And so if you, and I won't spend too much time talking about devices. I realize that the audience here is largely a theory-based audience, but I do want to spend a moment just to explain the basic concept of the device, because the rest of the talk is going to be quickly running through implementations with this. So the basic idea of a MOSFET transistor is that one has this light blue, which is silicon. The dark blue is a thin layer of silicon dioxide, which is an insulator. And then above it, we have a metal gate. Now, in CMOS technology, this metal is normally heavily doped polycrystalline silicon or other high dielectric constant metals. But here we just use simple aluminium metal electrode on the surface. Now, the other part of a conventional transistor is that you have a source and a drain. And like in a normal transistor, we used heavily phosphorus doped regions here for a source and a drain. And then when you turn a positive voltage onto the metal gate electrode, it draws electrons underneath the insulator. This is called the electron channel of the transistor, and this then connects the source and drain and turns the transistor on. So this would otherwise just be a normal transistor, but what we did in this device was we added 2 extra gate electrodes, one here, seen in this scanning electron microscope, and another one over here. And these electrodes, which were positioned under the top gate electrode, you can see the cross section here, and insulated from it, allow one to create potential barriers at this point and this point, which isolates a so-called quantum island or quantum dot, which has an integer number of electrons. And so this device then becomes what's often called a single electron transistor, because transport through this device is dominated by single electron tunneling processes on and off, because the capacitance of this island is so small that the charging energy for an electron to tunnel into this quantum dot is greater than the thermal energy when operated at low temperatures, typically 1 Kelvin or below. Typically, these devices are operated millikelvin. Over here on the right, what you see is the current through this transistor device as we change the gate voltage here. This is in volts on this top electrode. And you can see there are these peaks of current. And these occur every time we can energetically add 1 more electron into this quantum dot. So this technology is the technology we developed back in 2007, in which we've now progressed to make a variety of qubit demonstrations I'm going to be talking about, and which you know, we and others are looking to be a large-scale approach for quantum computing. It took a few years to go from developing these quantum dots and reducing them to the single electron level in a reliable way. But in 2014, our group, and this is some work done by our postdoc at the time, Menno Veldhorst. Menno's now a very successful faculty member at TU Delft. In this work, what we did was we configured one of these quantum dot devices, and I won't describe the fine details of the structure here, except to say that with the electrodes here, we were able to isolate a single electron inside one of these quantum dots, and we positioned it next to one of these single electron transistor devices for doing the spin readout. And on the left, we have here in this micrograph one of these on-chip microwave antennas, which allows us to apply an AC magnetic field, exactly as I showed for those donor qubits. But now, of course, we have no silicon atoms involved. This now, the electrons are confined purely by a surface gate electrode, like in a MOSFET. And so in this paper in 2014, we used, again, silicon-28, and we showed that it was possible to get high-fidelity Rabi oscillations of a single electron spin inside one of these quantum dots. And in fact, we showed that and this was the first measurement of fidelity, we showed that it was above 99%, obviously in the fault-tolerant regime. So a very important result. And in fact, this paper was published back-to-back with the atom paper, Andrea Morello's work on the single atom in enriched silicon in Nature Nano. I just want to again highlight, particularly for the theorists in the audience, just the similarity between this qubit, which has this metal oxide semiconductor stack with the electron spin bound under the gate. And here we see from a Pentium chip, this is 15 years old, a Pentium transistor with the metal gate. The oxide here is so thin you can't even see it. It's only 1.2 nanometers thick of silicon dioxide, and then the silicon channel below. So effectively, we're using exactly the same structures that are used in CMOS electronics. And I'll return to this at the end of the talk in terms of scalability. I described that it took us a while to move from the many electron quantum dots down to the single quantum dot, which we used for the demonstration that I just showed you of a single electron qubit in MOS. But in fact, this year, we published a paper here in Nature Communications, details here, from our PhD student, now postdoc. In fact, our PhD student, Ross Leon, just got his PhD announced today, so congratulations, Ross. And this is a very nice piece of work from his PhD. And what he showed in this paper is that one doesn't have to settle with just single electron qubits. In fact, we can operate qubits with many more electrons than that. And the reason that this is important is that one of the challenges of using the CMOS platform is that the silicon-silicon dioxide interface is not stoichiometrically perfect. So there will always be disorder at that interface, and silicon dioxide itself is a quasi-crystalline amorphous material, which means that there will always be disorder, which can upset the potentials that we want for our qubits. Now, if, however, we operate our quantum dots at higher electron densities, this can screen out the effect of materials-related disorder and make our qubits much more robust. So, without going into too much detail, what this paper shows, this is actually showing magnetospectroscopy of each of the electrons added into this quantum dot, all the way from 1 electron up to well above 30 electrons. And as we add an electron in, we find that the energy required to add it falls away because the capacitance of the dot is increasing. But we find that the energy has these jumps when we add the 5th electron, the 13th electron, and the 25th electron. And this is because our quantum dot is acting like a two-dimensional atom. It's a two-dimensional circular atom, and Fock-Darwin physics applies. So Fock and Darwin in the 1930s solved Schrodinger's equation for a two-dimensional circular potential, and that's exactly what we have here. And we have a shell structure in our 2D atom, just like one has in a 3D atom. And so the first 4 electrons fill in to so-called 2 valley states, spin down and spin up. So we have 4 electrons in the first valley, and then we jump up to a new orbital level in the 2D atom, and that can accommodate 8 electrons. And then then there are 3 orbitals in the next shell which can accommodate 12 electrons. And so our S electrons, we have 4, 8 in P states and 12 in D states. And what Ross showed in this beautiful paper is that when we are in the single valent states, so with 1 electron or with 5 electrons, when we have a single P electron occupied, or in 13 electrons with a single D electron occupied, we can observe excellent Rabi oscillations and very, very good coherence as well. And so what this means is that we can operate at higher electron numbers, which screens out disorder, and we don't have to worry about operating at this very low 1 electron limit. So it's a very, very important paper for us. Now, continuing on the theme of the issue of the reliability, performance, and fidelities of the qubits, I want to mention a paper that our group published last year in Nature Electronics. And in fact, this was work done in collaboration with Stephen Bartlett, who introduced me. Stephen and his team worked on a lot of the theory about this. So in this work, and the experimentalist who led this is Henry Yang, who's a faculty member in our School of Electrical Engineering now. Henry in this paper used pulse engineering techniques, which allows one to cope with low frequency noise in the environment, either due to slow charge fluctuations and other effects, so effectively in order to improve the fidelity of the single qubit gates. And with this, he was able to demonstrate a single qubit gate fidelity of 99.96%. So this remains the highest fidelity single qubit in a quantum dot system in any semiconductor system to date. And in this nice work from nice review in the same edition of Nature Electronics from Joe Emerson, he showed that our silicon qubits are now competitive with the very best ion trap and superconducting qubits out there in the literature. One of the things that Stephen Bartlett and his team showed was that we had reached effectively the limits of what could be done with pulse engineering here, and we were limited purely by the stochastic noise associated with background high frequency noise. Okay, so with we clearly have very high fidelity single qubits. What about multi-qubit systems? So again, I just put up this diagram showing this device that was used for the single qubit operation. It can also be used for multi-qubit operations. So at the bottom here, we have this single electron transistor structure. This is used to do the readout of the spins using the technique I showed you before. These red gate electrodes, you can see there are these 4 gate electrodes, G1, G2, G3, G4, each one an aluminium electrode, and each one of these electrodes can confine a single quantum dot underneath it. So if we zoom in, we see that we actually have additional electrodes which confine the electron wave function here at the left and the right, and it allows us to then have a row of quantum dots. So if I take a cut through along here through the qubit line, we see the aluminium gate electrode and the electron wave function in between. And we have a natural oxide barrier, insulating barrier formed by aluminium oxide in between, which creates a natural isolating barrier between our qubits. So it's a very, very simple structure. Effectively, one gate can confine one electrode. And here we show that in this device, we can control very high fidelity single qubits under each of those electrons just in a straight line. And I'll talk about extending this to 2 dimensions in a moment. But first, I want to show this important result now from 5 years ago, 2015. Again, Menno Veldhorst was the postdoc working on this in our group at the time, who did the experiments with Henry Yang and showed that it was possible to operate a 2-qubit logic gate using the same sort of device, just this linear chain of quantum dots using the technique I showed you. And the operation that was performed was a C0 gate. This was employed via a CZ. So the full protocol uses it's a combination of a pion 2 rotation, which is provided by the on-chip electron spin resonance from the microwave antenna, and then a CZ gate is performed. This is done by encouraging the two, effectively trying to force one electron to tunnel across to the other. That increases the exchange interaction between the two spins. So we actually operate this when we're doing one qubit operations in this experiment. It was done with exchange turned off, and then to do the CZ, you push the two electrons together, you turn exchange on, and then you separate them again, and you then perform another pion 2, and that produces a C0. And in this work we showed correlation between the spins, demonstrating entanglement between the two. Since that time, our team has continued to improve the performance of our 2-qubit gates. And last year in Nature, this paper from, again, Henry Yang, the lead postdoc, but also Wister Huang, who was our PhD student at the time. Wister's now moved to ETH Zurich to work with the group of Klaus Enslin. They demonstrated experimentally the first ever randomized benchmarking of a 2-qubit gate in silicon, and demonstrated a 98% fidelity in this case. I should note that the operation of this qubit is not the way we ultimately want to operate it in the long term, because this was done with exchange always turned on. And what we're currently developing is the ability to switch the exchange on and off with an interstitial exchange gate, and that allows us to do much faster 2-qubit gates, and we believe we'll be able to push that fidelity well above 99% using that. I should mention just one last talk about fidelity is that the readout fidelities have also demonstrated above that 99% threshold. This is some work from our former postdoc and PhD student Rushen Zhao, who's now at NIST in the US, and Tuomo Tantu, where they showed very high fidelity singlet-triplet readout in one of these chains of quantum dots. So I want to finish my talk now. So that's the basic physics of the operation and some discussion of where the fidelities sit at the moment. I should mention that other groups in Delft, the group of Lieven van der Sijpen and Menno Veldhorst in Delft and Jason Petter in Princeton have been pushing 2-qubit logic as well in silicon germanium, and with Menno Veldhorst also in the silicon-MOS system, and have demonstrated exceptional 2-qubit gate performance and operation as well. But I now want to turn to the issue of scaling this technology. And so one mention I want to make, although I won't talk more about it, is the potential to use nuclear spins coupled to these quantum dots as a potential memory element in the future. Although most, for example, the surface code doesn't utilize memory, there are some schemes that can benefit from having a quantum memory. And in this paper with our former postdoc Baz Henson, we showed, published this year, we showed that the background small number of silicon-29s that are still present even in isotopically enriched silicon, it's possible to operate a nuclear spin qubit on one of these silicon-29 nuclei. These can have very long coherence times, and then to act as a quantum memory, and this can be coupled with and entangled with the spin in a quantum dot device. So I just mentioned that for people who are interested to learn more. You can have a look at this paper if you're interested in quantum memory. But I want to move on now to talking about the use of just using the electron spins, as I've primarily been talking about for our quantum dots, and mention this paper that was done in collaboration with our colleagues at HRL Laboratories in Malibu in California. Particularly the theory work on this was done by Cody Jones. Cody's since left and moved to Google in Venice Beach, but Thaddeus Ladd and Mark Guy were key coordinators on this work. Thaddeus, of course, still at HRL. And so the conceptual work from Cody here was to design on a linear 1D chain of the type that I showed you that we make using our existing device, a very standard device structure for us, a full fault-tolerant logical qubit that could be made with somewhere between 14 or 20 electrons, depending on the level of performance required. 14 or 20 quantum dots in a linear chain, manipulated using spin resonance. So you could have an on-chip microwave line, as we've been using, and the readout process uses this singlet-triplet readout between pairs of quantum dots. And at the heart of this is a parity readout approach, whereby by having an additional 2 ancilla spins, where one can perform readout in the singlet-triplet basis, one can monitor the spin states of 2 data qubits in 2 separate dots, and either perform parity measurements, XX parity measurements or ZZ parity measurements, depending on how we perform the CNOT gates between the data and ancilla qubits. And I really just want to show this to show that, you know, it's a straightforward scheme of moving electrons between these 4 quantum dots in a linear chain, using the sort of device structure that we make in our fabrication lab at UNSW, and using the primitive readout protocols and ESR protocols I've described before. But if you're interested, you can take a look at this paper here. Now, one of the limitations, as you would know, for 1D linear chains, they've got limited connectivity, so the fault-tolerant threshold is very low, very, very high. One requires error rates as low as 10 to the minus 4, 10 to the minus 5, very, very challenging. And so ultimately, although this can be useful for doing early demonstrations of error detection, if one really wants fault tolerance, one needs to have the increased connectivity offered by schemes such as surface code. Of course, just giving an example here of the work from Fowl and Martinez and colleagues from a few years back. And this inspired our group to work on a design for a fully integrated SiMOS 2D architecture that could implement the surface code. The basic idea here is in the qubit plane to have these quantum dots in silicon-28, each one controlled by a gate electrode, and then an additional gate electrode in between to control exchange, this laid out in a 2D array. And one of the important aspects of this was that our team, Menno Veldhorst really leading this effort while he was still with us at UNSW, designed a full word and bit addressing architecture, circuit architecture that can be implemented in SiMOS, that could go all the way to implementing a full surface code using singlet-triplet readout. Now, I should mention that this is a very ambitious scheme. It requires incredible levels of integration. It's quite a number of years away, but there are many intermediate stages with simpler structures that are possible. And I now want to talk about manufacturability, because in 2016, in this landmark paper from a group at CEA-Leti and CEA Research in France, the measurements led by Silvana Di Franceschi, the device manufacturing led by Maud Vinay and her team, showed in a silicon-CMOS structure, these are called fully depleted silicon on insulator structures, showed the operation of a spin qubit. This was back in 2016. This is the whole-base spin qubit. And I should mention, and so this opens the possibility of using CMOS manufacture. This is a former CEO of Intel holding up a 300mm silicon wafer. And I should mention that Intel, just a month or so ago at an IEEE conference, presented their first work on an Intel fabricated qubit on their process line, operation of a silicon-electron qubit. Very, very impressive result. And so this is just reconfirming the fact that in manufacturing lines, it's possible to make qubits that can be high performance. To finish up, I want to note that getting all those wires into a chip is a real challenge, and in particular having those single electron transistor readout devices eats up a lot of real estate. And so this paper from 2013 from David Riley at University of Sydney and now at Microsoft showed that by just using a single gate electrode in a quantum dot system, it's possible by embedding it into an RF tank circuit to measure ultimately the spin state. In this case, it was a charge readout, but it can ultimately be done for spin using just a single electrode, significantly reducing the real estate. So for example, in one of our devices, if we have a pair of quantum dots, just by shuttling the electron between these, we can determine whether or not we have a singlet state which is polarizable, or a triplet state which is not polarizable, and this leads to a frequency shift in this RF tank circuit that can be monitored just by looking at the reflected signal on this single line. So it means that using a single gate, the same gate we use to make our qubit, we can also do readout of the qubit. And indeed, in this architecture paper from our group that we published with Monovalent back in 2017, this was this 2D architecture I showed before, that relies on the fact that we essentially have along one, effectively, one line of qubits, which is the effectively selecting the bit choice. All of those bits can be connected to one tank circuit, and we can read all of those out in just by sequentially reading them out. And then by having an array of these tank circuits, we can do frequency domain multiplexing in order to read out the entire 2D array very efficiently. And just last year, in a collaboration, in fact, with David Riley's group, we showed the first demonstration of single-shot spin readout in silicon using this dispersive technique. And I should mention that this was also demonstrated by groups at CEA and CNRS in France, and Michelle Simmons' group in Sydney, and also Lieven van der Sijpen's group at Delft did a similar demonstration all at the same time. So finally, this vision for an integrated architecture looks wonderful, but it's clearly very challenging. And one of the biggest issues is heat dissipation. So all of this superstructure of classical transistors and switching elements above the qubit layer is going to generate heat. Whether it is actually on the chip or it's on a chip nearby, a control chip nearby, it's going to generate heat. And in a really, one of the most significant breakthroughs from our group, really in the last 20 years, occurred this year in a paper from our postdoc, now staff member Henry Yang, mentioned his name a few times, this incredibly important result where he showed that one of our quantum dot spin qubits could still show high fidelity operation even at 1.5 Kelvin. Now, for those of you who are theorists not so familiar with cryogenics, 1.5 Kelvin may not seem like that much of a jump over 100 millikelvin, where we're all superconducting qubits, and to date all silicon qubits have been operated. But the reason this is important is that the cooling power, the ability to get the heat out of chips, goes up by a factor of 1,000 or more when we go to 1.5 Kelvin. And also we don't need the very, very expensive and sophisticated dilution refrigerator systems. It means that we can actually put our control electronics either on a chip next to the qubit chip, and there's many groups working on that, like, for example, David Riley's group for Microsoft, and also Intel and collaborations at EPFL with Eduardo Chavon are working on that to create control chips that can be sitting next to qubit chips, or indeed we can integrate some of the electronics on the chip, as I showed in our 2017 paper. And so ultimately, what we're working towards is a vision where we can turn a CMOS transistor reduce it to either the 1 or few qubit level, utilize the spin of those electrons in the quantum dots, manipulate them with radio frequency fields, couple them using simple electron-electron exchange, and then by using CMOS manufacturing, create large arrays, ultimately, hopefully 2D arrays, perhaps initially smaller arrays in order to do early stage demonstration and NISC demonstrations, and ultimately, hopefully, realize the promise of quantum computing at the billions of qubit level. And with that, I want to leave a picture of my team. This is the way we all communicate now, and I'm communicating to you now via Zoom. I'm sorry I have run a bit over time, but we're into a break, so hopefully we're still able I'm still able to answer some questions for you. I'm happy to stay on as long as necessary. Thank you again to the organizers, and thank you for your attention.
All right, thank you, Andrew. I'm sure there's virtual applause going through the internet right now. And we will take a few questions, even though we're running a bit up on time. Atsushi Mitsuo has been very patient. He was the one who had his hand up very early on in the talk. So I'll pass over to them for the first question.
Great.
You can unmute yourself and ask your question, Atsushi, if you want. Maybe we left it too long. We also have a question here from Quark Chen. If you want to go ahead and ask that question.
Maybe the unmuting's causing a problem. I had that problem on a call last night, actually. Someone just couldn't unmute themselves.
Quark Chen, are you there with a question?
I can see.
Yeah, I think his mic has been unmuted.
Yeah, I think that's the problem. Let me see if I can see. Is there questions in the chat?
Yeah, I think we're having some trouble. So you can type in the question and answer box or in the chat. I prefer the question and answer box if you want to type your question. I recognize that's a bit slower. Oh, okay. Here we go. Maybe you can read the question out loud. Andrew.
Yeah, sure, will do. Okay, so the question is, with millions of qubits to be controlled, you need high-speed electronics, which might make huge electromagnetic noise, which will cause decoherence. How will you deal with them? Yep, that's an extremely good question. And indeed, the issue of noise and crosstalk is one that it's going to be one of the biggest engineering challenges in terms of controlling many qubits. I should say that I mentioned earlier that there's already very substantial work going on in cryogenic control chips being done by Microsoft, David Riley's group, by Intel and collaborators at Delft and EPL. They recently showed some results of cryogenic control chips, and the issues of effectively microwave engineering to ensure that the amount of stray fields that are produced is one thing being dealt with. So one of the key questions is whether it's going to be possible to have the control chip actually integrated with the qubit layers, or whether it's going to be necessary to have it off chip and perhaps just having some interposer and having the slightly more noisy electronics nearby. One thing to note is that, of course, one can integrate filters into these chips as well, and that is indeed being done at the moment in order to minimize those EMI issues. It's also worth noting that the whole issue of EMI noise on chip is something that has had, many billions of dollars of investment in the conventional CMOS industry, and so it is something where there's a huge knowledge base that can be leveraged as qubit integrated circuits are created. And so it's definitely an issue, and it's one of the big engineering issues being faced.
And another question just in there from Christina.
Yeah. Hi, Christina. Thanks for the question. So I'll just read it out. You mentioned crosstalk. This is correlated noise, right? Do you plan to reduce and correct it? So understanding exactly how much crosstalk that there is in silicon qubits is one of the big next steps in research efforts, including our own group. So at the moment, there's been a little bit of early study of correlated noise. Certainly, if you have a remote EM field, it's going to affect a large number of qubits, and it is going to be correlated. So the desire to damp that out as much as possible is important. At the moment, it's not clear whether it's going to be the external noise which would be largely correlated, which is going to be most important, or the internal materials noise. There's no question that there will always be an element of materials noise, and that's probably going to be much less correlated compared with the external noise. I don't have any particular, I think that there are a variety of people around the world looking at ways to deal with correlated noise. That's not my particular specialty or field, so I won't comment on that aspect. But clearly what we're focusing on at the moment is understanding the extent to which the noise is correlated, and we do indeed have efforts in our group, and I know other groups around the world in silicon are looking at this as well.
I see. Okay, thank you. So it's basically, this is a non-Markovian noise, and I was wondering, because this is my field, I was wondering, but I'm doing it in theory. So we do have a way, the first way that encompasses any kind of non-Markovian noise, including quantum nature, non-Markovian noise. Mm-hmm. However, this to investigate it, you need in a lot of places inside the process, you need to access it and kind of do some tomographically complete measurements. And I was wondering, how realistic is this in a silicon?
Well, it's funny you should mention tomography, because as Stephen Bartlett would know, we've been working with his group in order to do further characterization and fast characterization, which could provide some clues. I think that the way I envisage this going is that there's still a very long runway of fundamental research to understand the sources of noises, mitigation techniques, and so on. And ultimately, there will have to be design of protocols and indeed characterization protocols as we move to large qubit systems. I mean, at a certain point, one needs, you know, a qubit processor with billions of qubits to have highly automated operation. And so really the job of the research scientists doing the experimental studies of qubits together with quantum information scientists and theorists like yourself is very important in order to try to find solutions that are going to go all the way up to full-scale systems. So it's certainly something that we're very aware of. And I mean, I don't know whether our host, Stephen, has any further comments on that.
None for me. And just in the interest of time, we've got one more question. Let's just move on from an anonymous attendee here.
Okay, so the question is, what are the temperatures for silicon-based quantum computing with nuclear phosphorus spins? Okay, so those spins, as it turns out, can survive up to extremely high temperatures. In fact, there was a remarkable demonstration some years ago from the group of John Morton at UCL with Collaborators, where at Simon Fraser University in Canada, where they actually polarized a qubit chip and took it out to room temperature and took it and then dropped it back down to low temperature and showed that the coherence still remained even after going up to high temperature. Now, the reason they had to go back down to low temperature was because the readout required low temperature. It was an optical readout in that particular situation. And so the limitations for nuclei is not the decoherence due to the temperature, it's the way you read it out. And the way that you read out nuclear spins necessarily involves coupling them to electron spins. And then once you're using electron spins, so really the limitation is what is the temperature where you can do reliable electron spin readout, as well as electron coherent control, and what is that temperature limit? So the answer to that is that it's something that we're still investigating. And in fact, I can't say it because we've got a paper coming out very, very soon, but not yet there. Hopefully we're going to post it on the archive before Christmas, where we're looking at operating readout devices at much higher temperatures. So at temperatures that could be approaching a few Kelvin, 4 Kelvin or so. But much above that, readout becomes quite difficult. But I think it is highly possible that all quantum operations, whether it be for nuclear spins or for quantum dots, can happen at the 1 Kelvin regime, which is very accessible and can take a lot of CMOS chip power. And it is not out of the question that you could even go to 4 Kelvin, although at 4 Kelvin, lattice-based decoherence mechanisms do start to cause problem with fidelities of qubits. So with that, I think, is that the last question I'm allowed to answer, Stephen, at least in this forum?
Well, and it's also, I think, the last one, at least the last one here in the Q&A. So everyone can join me virtually in thanking Andrew Dzurak for a fantastic talk. And I invite everyone back in 50 minutes from right now for the next invited speaker. Thank you very much.
Thank you. Thank you, everybody.
Thank you, Andrew.
Thank you. I hope that was okay. Sorry for eating into a bit of the break.
Oh, that's wonderful. It's a very nice talk.
Yeah, I mean, I am presuming that the majority of attendees are primarily theorists, and so I thought I'd keep it to a fairly high level and also try to give a bit of an understanding of the basic operation of these qubits rather than just rolling off a whole lot of recent stuff.
No, it's wonderful. I learned a lot because it's difficult for myself to just go through those literature. So with this talk, I can definitely get a much better understanding of the how the silicon quantum devices like evolved.
Mm-hmm.
Thank you so much.
And so this will be now available on your UTS hub of talks, right?
Yes,
so
yes.
That's
So
great.
we would also upload the video there,
Great.
so that
Fantastic.
people can come back and see it again.
Yeah.
And yes.
Fantastic.
Good.
All right. Well, look, I might say goodbye for now and log on a little bit later. All right.
Okay. Thanks. See you.
Fantastic. And thank you again. All right. Bye for now.